Okay, perfecto. So, buenos días, good morning to everybody. So, it's a really pleasure to start one new webinar for this Red Latinoamericano de Físico-Química Teórica. And so today we have the honor to present to Dr. Oriana Brea. It's from Venezuela, and actually she did the pregrado in chemistry in Universidad de Oriente in Venezuela. And later on, she did the master in computational chemistry in Universidad Autónoma de Madrid in Spain. And actually, it's really interesting because she was one of the people that used this Erasmus Mundus scholarship that it's really great for people that want to do some PhD in Europe. And she also did the PhD in Spain, Universidad Autónoma de Madrid. But also she do some experiments in France and using the beca para la formación de profesorado universitario. So right now she is in the group of FAMI IMO in Stockholm University. And actually she has one Bernard Green Foundation scholarships. So thank you, Oriana, for accepting this invitation. And
thank you for the invitation.
Hope that this is not the first time that you share your work here in this space. Thank you.
Okay. Thank you very much. Actually, thank you for allowing me to be part of the amazing group of speakers in the webinar. So today I will, before starting my presentation, I would like to introduce myself. So as was said before, I'm from Venezuela, from Margarita Island. From Margarita Island, and I studied there. The pointer is okay, maybe better now. Okay, so I'm from Margarita Island in Venezuela, and I studied there the bachelor in chemistry. And when I finished the bachelor, I moved to the TCCM, as was said before, with the Erasmus Mundus scholarship, which I highly recommend it. I think it's still open for this year fellowship. And after finishing my master, I was lucky enough to stay in my group, and we decided to do also the PhD, but this time we did it in Cotutel with Université Paul Sabatier. And then after my PhD, I moved to Stockholm University. Actually, this is a picture of our lab now in winter, where I'm still as a postdoc researcher. And during this time, I have done different type of chemistry, always computationally. So for instance, we always have a study reactivity, but we have a study reactivity in different environments. So during my PhD, I was studying gas phase chemistry, especially with beryllium. And the idea was to show that you can introduce a toxic element that general experimentals are not happy to work with, but you can give very nice properties to the system, and computationally we can work it without the toxicity problem. So for instance, we show that by joining a beryllium moiety, you can generate automatically radical species without any energy barrier, or that you can create a sigma hole that normally it's not formed in fluorine. Fluorine doesn't have a sigma hole, and in this case, we can create it with beryllium. But then, as I said before, I moved to an organic chemistry department, and then we started working with reactions in solution. So two of the projects that we've been working right now is one, trying to understand the reactivity of and stability of benzodiazole transfer reagents. So these benzodiazole transfer reagents are special because of this hypervalent bond, and it's special because then this type, the group that is attached, in this case, the 3-fluoromethylthio, is easily transferred and selectively transferred. The issue is that sometimes they are stable in the hypervalent form, and sometimes they are stable in the open form, as in the case of the SF3. I lost the pointer. Well, here, as the case of the SF3 reagent, that sometimes is more stable in the open one. And it's not easy to understand. It's not known why these different type of behaviors, and we studied from the computational point of view, and we explain why one exists in the hypervalent and the other exists in the open form. And another project that we're working also in now in solution is about sulfoxidation reactions catalyzed by vanadium. So we want to understand which is the role of the catalyst on the rate of the reaction and also on the selectivity of the oxidation over oxidation. And we're also working on reactions in confined space. So we're studying reactivity of molecules inside of molecular nanocapsules, like in this case, for instance, this is the inhibition of the thermal decomposition of N-nitrosamides, or we can study the catalysis by vanadium compounds in a cage form. But today I would present my work on the reaction in solution. So we have either, so it's a project about hypervalent and the project about sulfoxidation. And even though these are two different projects, they are nice because they can show how we can use computational chemistry to improve a chemical reaction from 2 points of view. Here, we're going to improve the synthesis of the reagent that later on is going to be used for doing the catalysis, while in this case, we're going to try to understand the role of the catalyst and try to use this for improving the reaction. So here's the computational scheme that we use in the group, and here is a review that was written by my boss and collaborator that explains very well the methodology that we follow. So generally what we do is that we start with experiments that either we find in the literature that are special or the result is intriguing and they cannot solve this issue from an experimental point of view, or some colleagues approach to us and tell us like, this is interesting to consider. So we take these experiments, we build our reaction profile. So here is the technical details for the computational chemists in the audience. And then after we build the reaction profile, we analyze the different barriers. So we take the key transition states and we try to understand the difference in these barriers. And we do it using different types of methodologies. For instance, we can use the composition analysis, we can use MO analysis, we can change the substituent and so on until we understand which is the difference between the barriers. Then we try to improve this energy profile. And if we're lucky enough, maybe our ideas go back to the experiments, but that's not always the case. So now I'm going to start with the first project that I talked before. It's a project about the hyperbalance reagents. So this is the two most well-known examples about how the synthesis of these reagents can go wrong. In the top, we have the 3-fluoromethyl reagent that it's synthesized, it's easily synthesized, and it's very well known. It's known as Stockholm reagent and it's highly used. You can even buy it. And the synthesis starts with the chlorobenzodiazole reactant that is treated with potassium fluoride. So we have a displacement of fluorine by chlorine. We arrive to the fluorobenzodiazole intermediate, and then this reacts with the Rupert-Prager's reagent to arrive to the 3-fluoromethyl hypervalent form. In the other case, in which we have the SF3, so we're just changing the sulfur group, we also start with the chlorobenzodiazole. Now in this case, we treat it with silver SF3. And in this case, initially it was thought that this was a hypervalent form, but later on it was discovered that no, that it was the thioperoxide. And even though the two syntheses are quite similar, the two products are different. And we wanted to understand why. So as I said before, we started doing the reaction profile. And in this case, we only consider the second part of the reaction because it's in this part where you either go to the hypervalent or to the peroxide form. So here is the energy profile. And then now I will walk you through it. So our starting point is the fluorobenzodiazole in complex with potassium fluoride. And then from here, the first step is a nucleophilic attack of the fluorine from the salt to the silicon center. And we can see here an animation of the transition state. Here is the nucleophilic attack. And then we arrive to INT1, in which there is a hypervalent silicon. So if you like hypervalent chemistry, you have hypervalent iodine, hypervalent silicon, everything in this intermediate. And then from this hypervalent silicon intermediate, the next step is the a heterolytic dissociation of the silicon trifluoromethyl bond that takes place as in this animation. So we can see here the dissociation of the bond, and we arrive to INT2, which is a very special intermediate. This is a carbon ion that is stabilized by the interactions with the potassium salt. And from here, the next step of the reaction to arrive to the hypervalent form will be a nucleophilic attack on the iodine and then dissociation of the iodine fluorine bond. We can see here that the animation of this transition state. And from here, we arrive to Tony reagent and the catalytic cycle is closed. But if from INT2, which is a carbon ion that is very reactive, we could also imagine that we can attack on the oxygen and form the ether isomer. We also calculate the barriers, and you can see they are much higher. So this energy profile shows why we are favoring the less thermodynamically product by kinetic controlling the barriers. So the other thing that you could imagine is that once you are in the hypervalent form, you can do the isomerization to the ether, which was computationally studied previously by Schaeffer and collaborators. And the barriers are around 50 kcal per mole. But what we did was considering if potassium fluoride could catalyze this reaction. And we found that indeed decreased the barrier, but it's not enough. It decreases from 50 to 45. So this isomerization doesn't take place. Therefore, we're able to explain the stability of Tony reagent. Now let's go to the next synthesis. We know we are able to explain this synthesis. Now what we want to explain is the second one. Can we explain both reactants? So once again, we study the energy profile. The starting point is the chlorobenzodiazole in complex with silver SCF3. And the first step of the mechanism is a heterolytic dissociation of the chlorine-iodine bond that ends in an intermediate that is an intimate ion pair, from which in the next step, there is a nucleophilic attack of the SCF3 over the iodine, forming the hypervalent form of the SF3 reagent in complex with silver chloride. What we expect from this intermediate is that silver chloride will precipitate, and we're going to have in solution the hypervalent form of the SF3 reagent that can go in complex with another molecule of silver SCF3, and this will start the second part of our mechanism. We're choosing this as a zero because the precipitation of silver chloride is going to be a very exothermic process, so it's easier if this second part with this new supercomplex is our new zero. So the first step of this second part of the reaction is an isomerization of the oxygen iodine SCF3 bond. So in the hypervalent form, this is in a trans form, and then we isomerize to a cis isomer. Actually, this isomerization is catalyzed by silver. It has been shown that can be also catalyzed by other metals like palladium or zinc, because in the absence of the metal, it's associated with very high energy barriers. And then from the cis isomer, the next step is a nucleophilic attack of the sulfur over the oxygen and dissociation of the iodine oxygen and iodine SCF3 bonds. And then we arrive to the thioperoxide form, and later we close the catalytic cycle. In this case, what we found is that the energy barrier for the isomerization decreased by 10 kcal per mole when it's compared with the reaction in the absence of silver, showing the catalytic effect and the relevance of the silver metal in this synthesis. So when we had the energy profile and we were able to understand why in the case of CF3, you arrive to the hypervalent form, and in the case of SCF3, you arrive to the thioperoxide, and the relevance that the two metals, potassium and silver, had in the synthesis, we started to think, how can we do to promote the hypervalent form and to avoid this isomerization? Can we propose to do the reaction at lower temperatures so that this barrier raise and you can isolate the intermediate? Can we do a substitution in this functional group such that this nucleophilic attack has higher energy barriers? And just when we were writing everything up and trying to find new ideas, the group of Sun published the first hypervalent SF3 reagent. So the SF3 in the thioperoxide form was published in 2013. This came up in 2020. So it took 7 years for finding this reagent. The synthesis is very similar. The main difference is that they changed the benzodiazole skeleton for an N-acetyl benzodiazole. So we have this new group. And you treat it with silver SF3 and you arrive to the hypervalent form. And what we did, we repeat the calculations and we found that both the isomerization and the direct formation are kinetically blocked. The energy barriers are 36.9 kcal per mole. And this is why this isomerization is not taking place. And the reason for this is associated with this acetyl group. The acetyl group creates a pi cloud around all the N-acetyl moiety, making the nucleophilic attack to be much higher in energy. Actually, we replace the acetyl group here for a methyl one, and the energy barrier decreased by 10 kcals per mole. So we were able to explain why the SF2 reagent exists in one form, why the CF3 exists in another one. We were able to propose catalytic cycles that explain both of them. And this allows you to do rational design of synthetic routes. And one of the examples that I'm going to show, that is what we're currently working in this group, is the CF2 bromine reagent. So the synthesis for the 3-fluoromethyl-1 works and it's very well known, but in the moment that you exchange one fluorine atom by one bromine, the reaction doesn't work anymore. So this was written in the paper that they did various attempts, that they were unsuccessful and that the reasons are not clear. So we have repeat our energy profile in the case of the CF2 bromine. And what we have found is, as I mentioned before, in the case of the CF3 reagent, there is a 3-fluoromethyl carbon ion, there is a very important intermediate. While in the case of CF2 bromine, instead of a carbon ion, we have the formation of a carbene. So the chemistry is going to be completely different for these synthetic pathways and for these two reagents. In this case, it will go through nucleophilic attacks, while in this case, it's going to be more for an insertion point of view. And that's what we're working right now, to try to propose a synthetic pathway that's such that this the CF2 bromine reagent is possible to be synthesized. And with that, I will finish this first part. If you're interested and you want to read more, the paper was published at the end of last year. And I'm going to move now to the sulfoxidation reaction part. So this is the reaction that we want to study. You have a sulfide that you treat with a peroxide and you obtain a sulfoxide, but this can be over-oxidized and then you obtain the sulfone. And the reason, and the problem with this reaction is related with the rate. Normally, just with the peroxide is very slow. The chemoselectivity of the sulfoxide over the sulfone is also an issue because you want to selectively form only the sulfoxide. And then the non-selectivity is also an issue. So even though I'm drawing the sulfides as a plane, this, the carbon oxo group can be in the back and you can have the lone pair of the sulfur and then you can have the two possible enantiomers. And for that reason, you use catalyst. And in our case today, I will talk about vanadium catalyst. So the reaction that we want to work is the reaction of thionisol. The peroxide is cumene hydroperoxide. And the idea is to obtain this sulfoxide and to avoid the formation of this sulfone. So the first thing that we did was to study the reaction in the absence of a catalyst, so the background reaction. So the reaction takes place concertedly. We can see that in the same step, you break the OO bond, you form the oxygen-sulfur bond, and the proton is transferred from the terminal oxygen to the non-terminal oxygen with a barrier of 26.9 kcal per mole. So what we want to do now is to calculate the reaction in the presence of this vanadin train catalyst. What we know from the experiment is that after 180 minutes of reaction, they obtain a yield of the sulfoxide of 16% and a selectivity of 89%. So we started to do our catalytic study, but before that, we checked in the bibliography, and we were lucky because this reaction catalyzed by vanadium has been widely studied because the vanadium peroxidase enzyme is able to do this reaction, and it's very efficient, and there's been several computational works trying to understand how the active site of this enzyme works. So the mechanism they propose is to start with you oxo-vanadium catalyst, the peroxide enters, you protonate the oxo group and coordinate the peroxide to the metal, then transfer back the proton, arrive to a vanadium peroxide intermediate, and it's this vanadium peroxide that does the catalysis. And this has been associated with the rate determinant step of the mechanism, the last step. Our issue was that when we tried this mechanism with our vanadium train catalyst, it didn't work. The barriers were higher than 30, in some cases we arrived to high barriers of 50 kcals, and we have to propose a different mechanism to that proposed for the enzymes. So here is the mechanism that we are proposing. As again, I will walk you through it. So we start with our catalyst. The vanadium peroxide enters, but now instead of protonate the oxo group, we protonate an equatorial ligand, and we coordinate the remaining part of the peroxide to the metal. So here is an animation. I remove the big bulky groups from the animation so it will be easier to see the reaction coordinates. So we can see here the proton transfer and the coordination of the peroxide to vanadium. Then we have a second step that is associated with a low energy barrier. There is the coordination of the non-terminal oxygen to vanadium, and we arrive to INT2. And now from INT2, the sulfoxidation takes place. This step was found to be concerted. In one step, we form the sulfur-oxygen bond, and we dissociate the oxygen-oxygen bond in an autosphere mechanism. And we arrive to, we release the product, the sulfoxide, and we arrive to a third intermediate in which the remaining part of the peroxide is still coordinated to the metal. So the last step of the reaction to recover the catalyst will be to transfer back the proton, release the side product, and then we recover our catalyst. So we found an energy profile in which the energy barrier is lower than the background reaction. It's lower by 5 kcal per mole. So this means that the catalyst is making the reaction 10,000-fold faster than in its absence, which is in agreement with the experiment. And we also find that the rate determinant step of the mechanism is the protonation of the equatorial ligand and not the sulfoxidation step, which is different to what has been proposed for enzyme catalysis. But now the last part that we need to test of our mechanism is about the selectivity, because once we arrive to INT2, there are two options. You can either oxidize the sulfide and you obtain the desired product, or you can over-oxidize the sulfoxide, obtaining the sulfone. So here's an animation of both transition state now with all the bulky groups included. So here is a TS for the oxidation, and here is a TS for the over-oxidation. And the energy difference between them is 0.7 kcal per mole, so it's almost nothing. But in the experiments, they found that that would give a selectivity of 90%. So there's another important issue that is going to have an important role in this selectivity, that is the concentrations. So initially, you're going to have a high concentration of the reactant and a lower concentration of the product. And if for doing kinetic control, you stop the reaction, you might favor the oxidation of the reactant. So if we want to study change in the concentration, our energy profile is not enough. So we have to move to do kinetic modeling. So what we did with kinetic modeling is to take our energy profile, take each one of our energy barriers, and transform these in kinetic constants by considering the Airing equation. And then we can build a set of equations, and we can use Copasi to run different trajectories. So what Copasi does is it calculates the change of your concentrations with time. And in our case, we decided to run our simulation until 99% completion. In the experiments, they stop the reaction at 180 minutes. In this case, it's like you leave the reaction overnight and you come in the morning to check what is the result. So as we're going to measure how the concentration changed with time, we need initial settings for this concentration. And we started as was proposing that as was done in the experiment. So we start with 1 equivalent of the peroxide, 1 equivalent of the sulfide, and 1.5 mol% of the catalyst. And the type of information that you can get from Copasio from this kinetic simulation is this, for instance. We start at the beginning, we have 1 molar of the peroxide and 0 molar of your product. And with time, all the peroxide will go to 0 and it will transform in the alcohol and in the sulfoxide. So we were using this tool to understand if our reaction profile obtained from DFT was able to replicate the selectivity. So here are some of the information that we got. I've lost. Okay, here. So for instance, here I'm plotting the yield of the sulfoxide against selectivity. So here is the selectivity is says at the end of the amount of product that you get at the end, how much is the sulfoxide and how much is the sulfone. So we can see that at the beginning, we have no yield of the sulfoxide and of course a high selectivity. And then with time, this starts to change and we arrive when the reaction goes to completion, we arrive to a 63% yield and a 78% of selectivity. And the same can be done with the conversion of the reagent. We start with a small conversion, a no conversion of the reagent, and it starts to increase. And you can see that at the end of the reaction, the maximum conversion that you can get of the reagent is 80%. It will never be 100 because part of the peroxide is used to oxidize the sulfoxide. And now this graph allows us to do a direct comparison with experiments. So we know from the experiments that at 60% yield, they obtain a 90% selectivity. In our case, at the 16% yield, we're obtaining 98% selectivity. So even though we are overestimating the selectivity of the reaction, we are having the right trend. Our reaction profile is able to predict that the oxidation is going to be favored over the overoxidation. So now we can use this kinetic modeling to try to optimize the reaction, because if you can stop it at 180 minutes, you have a good control of the selectivity, but your yield is just 16%. So our idea was to find a way in which you can improve the yield but without compromising the selectivity. And the first thing that we did was to study the initial concentrations, the effect of initial concentrations. So in this graph, what I'm showing is what happens if we keep the concentration of the peroxide a constant of 1 mol, and then we start changing the initial concentration of the sulfide. So we found first that there is a region in which the selectivity is a constant, is close to 0. And this is a region in which you have twice as much of peroxide. So you have enough reagent to oxidize both the sulfoxide and the product. And then after this 0.5 concentration, you start to see that the selectivity improves until when we have 5 equivalent of the reactant compared with the peroxide, we arrive to a selectivity of 98%. We can do the same the other way around. So we can keep constant the sulfide initial concentration at 0, and then we can start changing the one of the peroxide, and we found an opposite behavior. So while we increase the concentration of the peroxide, the selectivity starts to decrease until once again we arrive to a region where there is twice as peroxide as the sulfide, and then you can oxidize both the reactant and the product. So at this point, the first time I saw this graphic, I was very happy. So, okay, you just need to put 5 times more of the sulfide, and then you're going to have almost 100% selectivity, and you're going to have a 99% conversion. But the problem is that if your sulfide is not a cheap sulfide, you don't want to risk putting extra. So it's from a money point of view, is not the best solution. So the next option would be to try to, how can you play with the energy barriers? And that's what we did. So we changed the energy difference between the over-oxidation transition state and the oxidation one. So what this means when you have negative values is that the energy barrier for the over-oxidation is below the oxidation one. And the opposite, when you have positive value, then now the over-oxidation barrier is above the oxidation one. And we can see that when the over-oxidation barrier is very low, then it's going to be favorable and the selectivity is going to be close to 0. And then we are going to see that this starts increasing until for a delta G value of 4, we have almost 100% selectivity. And the same happens with the yield of the sulfoxide. Initially, you are favoring the over-oxidation, so you have a very low yield, and then it starts increasing until it reaches a maximum of 98%. So this seems, if you're able to change this barrier onto a plus 4 kcal per mole, then you have it. You are going to have a perfect yield and a perfect selectivity. But how easy is this to do? So I showed before the results for this catalyst in which we were having a delta G of plus delta G of plus 0.7, and we will reach a selectivity of 78%. What happens if we remove these bulky ligands and we just substitute by a methyl one? The delta G value decreased to minus 0.3, which corresponds with a selectivity of around 43%. And it shows how you can modify your catalyst by adding different bulky groups, which will increase this energy difference and therefore keep pushing towards having 100%. So with this, I would like to conclude this second part. So we were able to find a catalytic cycle that was catalytic compared with the background reaction, that the energy barriers were lower than that of the reaction in the absence of the catalyst. And more important, we found that the right determinant step of the reaction is the protonation of the equatorial ligand and not the sulfoxidation, as most of the people believe. Because then if you're going to try to optimize the reaction and you focus on optimizing this step, nothing is going to work because the right determinant step is the initial proton transfer. We were also able to use kinetic modeling to show that the sulfoxidation is favored over the oxidation, and we were also able to explain which is the role of these bulky groups in the catalyst. So what we are currently doing is trying to build up the case to understand which is the effect of confinement on this reaction mechanism. And with this will allow to do rational design of these catalysts and of these reactions. And with this, I would like to finish. I would like to thank my boss, Fami Hima, and Professor Kalma Sabo for his collaboration in the project of hypervalent iodine, to Fami's Himos group, and to the Brenner Foundation. And of course, thank you for your attention.
Thank you, Oriana. We will now have 15 minutes for questions. Any member of the audience may ask questions to the speaker by selecting the raise hand button or by sending a message through the chat, either Zoom or YouTube. So let's begin. Manuel Ortuno.
Hi, can you hear me?
Yes.
Yeah.
Okay, so thank you
Hola,
very
Manuel.
much, Oriana, for the talk. And I have a question about the first part.
Sure.
Yeah, I'm always afraid of this potassium without any solvent coordination around. So have you considered like explicit solvation for these cations?
Yes, I didn't want to show it today because otherwise it was going to be very, very long. So yes, we consider the solvent, and it doesn't play a role in this part of the initial compound, but it does play a role in this intermediate. Actually, there is another possible pathway here in which the solvent donates a proton and you release HCF3, which is a competitive pathway that could explain why this synthesis depends so much on the type of the solvent. So yes, we did consider it.
Okay, thank you.
You're welcome.
Now, Gabriel Merino.
Thank you, Oriana. Very nice talk. So my question is related to the level that you use for your computation. So why you select Bit-Relief? So my question is because, as you know, Bit-Relief is parameterized only for organic systems, and here you are using several atoms that are not considered for this parameterization. So I guess you did a species of validation of your methodology to make all this computation. So this is my question.
So the reason is that I'm lucky to be working in a group that they've been working with hypervalent iodine chemistry, metal catalysis. So they have used palladium, they have used zinc, they have used several metals, and this benchmark was done for me. So they know that it works and that you get reliable barriers with Bit-Relief for this type of metals, that for this type of chemistry, it works.
Yeah, but you know that maybe it's because there is not a real, it's not because it's you have a correct answer, it's because there are several cancellation of errors.
Yes, yes.
Perhaps for the previous system is working, but you don't know for this system that you are studying right now, no?
Yes, I'm not going to say that I did an extensive benchmark, but we did test some other functionals. So for instance, we're not only just functionals. In the case of the vanadium project, for instance, we also consider which is the amount of the Hartree-Fock exchange that you're including, because it has been found that sometimes for redox reaction, this is also important. So I did test, not an extensive test of hundreds of functionals, but we did test if our barriers were going to change, if we were having different behavior, and now the results were solid in every case, which is in agreement with what have been seen in the group in the last years.
Okay, thank you.
Manuel Ortuño has another question.
Hi again. Yes, so it's a follow-up on the benchmark. I guess for the energy, you use like a triple zeta with diffusion functions, but do you consider diffusion functions during optimization since you have fluorine with negative charge?
For instance, I didn't go very much in details. In the case of the first project, the hypervalent, like we were having so many charged species, everything was optimized in solvent. And they did test other basis sets, bigger and smaller for the geometry optimization. I consider Popple basis sets, different basis set I consider different, and different pseudo potentials, and there was not much change. But it was important in this project for the hypervalent that you have so many charged species to do the geometry optimization with solvent.
Okay, thanks.
Carlos Torres, who is watching us on YouTube, has a question. What software do you use to create the kind of animation that you showed in your presentation?
This is a local software of the group, so it's not available. It's not available. There's no any repository where you can download it. I'm sorry.
Okay, Julio da Silva says, very nice presentation, Oriana.
Thank you, Julio.
Kinetic modeling, do you include temperature effects over the calculated rates? And can you explain how you get selectivity from your kinetic modeling?
So yes, because actually let's go there. The reaction was not performed at room temperature. The reaction was performed at 0 degrees. So yes, I was included it. You do it when you change your energy barriers to kinetic constants, then you include there the temperature, and you also include it in the program. And then how you do it with capacity basically is that after you finish your trajectories, you at the end or at the moment that you want to choose, in our case, we ended at 99%, you know how much of the products is produced. So at the end, you know, if you start with 1 molar of each reagent, you know how much of that went to the sulfoxide and how much went to the sulfon. So then you can just do a difference between them and you calculate the selectivity. It will be the concentration of the sulfoxide over the sum of the sulfoxide and the sulfon, and then you get the selectivity.
Margarita Bernal has the following question. Thanks for a very interesting seminar on a topic I am very ignorant. I would like to know how do you analyze and characterize the hypervalent atoms? Just geometric factors, or do you use other indexes?
So actually, that's an interesting question on how this project started. So when we started this project, the idea is that we really believe that the stability of these reagents was associated with the nature of the hypervalent bond. So I did a lot of bonding analysis for this hypervalent bond. Homolugmo, MOs. I did a lot. I built the potential, the electrostatic potentials, considered the difference on the sigma hole of the iodines in each. I did a bunch of analysis, and we found that none of these trends was able to explain the difference between the stability. And then in that case is when we say, well, maybe this is associated with the synthesis and what is in the solution. And that's when we decided to go for the reaction profiles. And then in this case, it's just reactivity. It doesn't play a role anymore, the nature of the hypervalent bond, but it's about reactivity, about how potassium in the first case is not able to catalyze isomerization, but silver is able in the second one. And that's the difference between both. Unfortunately, was not related to hypervalent bonds that we could then use for predicting, but it was more related with the synthesis.
Any other questions? We still have time. Gabriel Merino.
Oriana, I have another question. So in your mechanism, sometimes you have two intermediates that are not connected with the transition states. Why?
Which? Where?
I don't remember. So in this one, for instance, let me remember. If you move some behind this one, for instance, no? So here, so in the first step, you have two local minima, and you don't have in the first step a transition state. And when you remove 5 and 3 in the last mechanism, you also don't have transition state. So why?
So in the, well, there are two different reasons. So in this one is because there's no barrier. So what I did to show this was doing a scan of the iodine chlorine distance, and I would just arrive to an asymptotic behavior that we arrive to 10.9 without any energy barrier. So that's why there's no any transition state.
But in what surface?
Sorry?
Sorry, Gabriel, I interrupted. Go ahead.
Yes, please, Gabe.
No, I was asking in what surface you don't see a barrier, because in this case here,
yes.
it could be.
In this case, there's not a barrier.
Yes,
in this case, there's not a barrier, but in this case, it's just a ligand exchange. So you don't calculate barriers for that. So this is you're just exchanging one ligand for another one, and there's no any barrier. But in this case, it's true. I'm not plotting a barrier because you just increase the distance, without any energy barrier. Probably if we were able to do the geometry optimization, including all the effects like solvent, the Gibbs free energy and so on, I will be able, but in this case, it just go up and that's all.
I don't know.
So that was my question, because like your plot here says relative free energy, which I would assume is Gibbs free energy. And that's why I think Gabriel was also asking the question is, like if you have, how is the entropic penalties that you might have, or if you may have a barrier in the enthalpic profile, but not in the Gibbs profile, that kind of thing.
Yeah, so, exactly. Yeah, because perhaps in the energy, not in the free energy profile, your intermediate, it's lower in energy than the reactants, no? So when you include the entropic effects, so you increase the energy of intermediate one. So it means that intermediate one doesn't involve in the mechanism. So I suggest to remove from there, no?
Well, it's well, you could remove it, but it's also a way of showing to people how the reaction goes, and that you don't just go from here to do the nucleophilic attack. So you go step by step. And actually, if you do the infinite dissociation of this ion pair, if you want to consider this as a limit barrier, is around 20 kcal per mole. So that's why we are not worried about if we are underestimating or if we're missing. But it's just more a visual effect how this reaction goes. And also because we don't know in the future if this synthesis is then studied in a different environment. If, for instance, we have seen that in the case of supramolecular catalysts, these type of intermediates might be able to be isolated. So it's extra information that maybe in the future might be useful for someone or not. So we believe that it's important that we provide all the findings that we find.
So building on Manuel's questions from earlier, that you have evaluated some of these with larger base sets, but like now I'm a little bit confused here. If you did the geometry optimization of these intermediates in solvent with these larger base sets as well.
So yes, I did. Of these intermediates, probably exactly this one, I really don't remember. I don't think so. But yes, I did also the geometry optimization, especially for sure of the ones with the carbon ions int2. We did it with larger basis sets and with the solvent, yes.
Thank you. Great talk.
Thank you.
Now we will have the last question. Alfredo Granado says, how did you define your transition states in this reaction? I was wondering if you use Gaussian program, how you define the transition states?
I'm not sure if I'm getting what it means to define the transition state. So yes, the calculations were run with Gaussian, and generally you're trying to find the best possible guess of your transition state, and then you use a transition state geometry optimization. That's how I do it. I don't use this QST2 or QST3 method of Gaussian, that I don't know if that's what maybe he was implying. I don't use those. I just trying to find the best guess for my transition state, and then for me doing the geometry optimization of the DS.
Okay, thank you. Well, we are done for today. Thanks to our speaker and everyone present for joining us. Gabriel, would you like to say a few last words?
So thank you again, Oriana. So very nice talk, and I hope you
thank you for the invitation.
Share more results in the next meeting. So thank you. Muchas gracias, Oriana.
Gracias.
Bye. So I guess it's everything. So you can check the next webinars in our web page. So please, Jessica, if you can copy and paste the website from our web page, so maybe it's useful. And so we will send more information for Twitter for the next webinar. So thank you very much.
Thanks. Bye-bye.
Okay, bye-bye.
Send more information for Twitter for the next webinar. So thank you very much. Terminamos.
Thanks. Bye-bye. See you.